You're scrolling through a beautifully optimized app. The animations are fluid, running at 60 frames per second. Then, the interface stutters and the scroll jumps. The glass begins to heat up against your palm. The UI stops responding to your touch, and then the screen suddenly cuts to black. To protect the integrity of the device, the iOS kernel has just executed your application. This forced termination happens because the app exceeded its strictly allotted share of random access memory, or RAM. Software memory is a living ecosystem. Inside your phone, millions of digital objects are born to render a profile picture or play a sound. They do their job, and then they are supposed to die. Catastrophic failures occur when microscopic flaws in the code prevent these objects from being deleted. They haunt the memory graveyard, refusing to let go until the entire system collapses.
To understand why these immortal objects become immortal, we have to look at the governing laws of the operating system. This is automatic reference counting, or ARC, iOS's accounting system. As parts of the app rely on an object, ARC increases its reference count, a permit to exist. When dependencies are severed, the count drops to 0, and ARC immediately reclaims the physical space. This creates a balanced digital economy, where memory is borrowed, utilized, and then instantly returned for other tasks to use. However, this entire system is predicated on the idea that objects are capable of letting go. If two objects become mutually dependent, the accounting logic breaks. Consider a standard architectural pattern, a user object that needs to load and display a profile object. Here, the user holds a strong reference to the profile, and the profile holds a strong reference back. When you swipe away, the system signals for deletion. Arc attempts to delete both, but neither count reaches 0. They're trapped in a retain cycle. They have become immortal. They are no longer reachable by the app, but they cannot be cleared from the hardware. While one cycle is small, a user navigating a deep feed can generate hundreds of these orphaned pairs in a single session. This is a memory leak. Thousands of objects pile up in the darkness, silently consuming the device's finite RAM, until there is no room left for the app to function. This mounting pressure eventually triggers a total process termination. The app vanishes, and the user is dumped back to the home screen, all because of 2 lines of code locked in an unbreakable embrace. To solve this, developers have to change the physics of how these objects interact without breaking the connection required for the app to work. We fix the cycle by declaring one of these connections as weak. A weak reference allows an object to see its partner, but it explicitly does not increase the reference count. It is a connection that doesn't create an obligation to stay alive. Now, when the screen closes, the user's count drops to 0 and it dissolves. With the user gone, the profile's last remaining connection is severed, and it is also reclaimed by the system. Engineering at this level isn't just about how components connect, it's about deliberately architecting how they detach. Mastering memory saves an app from collapsing under its own weight. But even a clean system faces a new threat: race conditions, the data corruption that occurs when multiple background tasks try to modify a single object at the exact same millisecond. Next time, we dive into the mechanics of swift concurrency.